How often do we think that the observable universe is only 5% of what exists? The rest of the cosmos is shrouded in the shadows of dark matter and dark energy, phenomena that baffle scientists and fascinate the curious minds of our world. In our quest to unravel the mysteries of the cosmos, we encounter anomalies, strange signals from deep space, unexplained celestial formations, and mysterious cosmic events that challenge our basic understanding of reality. Join us as we explore these unexplained anomalies of the universe. Among the many mysteries that continue to baffle scientists and astronomers, dark matter and dark energy top the list, posing serious challenges to our understanding of the cosmos. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible to our current technology. Its existence can be judged by the effects of gravity on visible matter. For example, galaxies rotate at such high speeds that, based on their apparent mass, they should be separated. Yet they persist, leading us to believe that there is a large amount of unseen matter exerting a gravitational influence. That's the dark matter business. Dark energy is a more mysterious phenomenon. Comprising about 73% of the universe, it is thought to be responsible for the rapid expansion of the cosmos. Although we see galaxies moving away from each other, their speed is increasing, contrary to expectations based on gravitational attraction. This suggests that there is a mysterious force separating galaxies, and we know very little about its nature and origin. Some theories suggest that dark energy may be related to cosmic energy, but its true characteristics remain elusive. Another interesting unexplained phenomenon is fast radio bursts, or FRBS. These short but powerful radio waves have been detected in distant galaxies and last only milliseconds. The source of these bursts is still unclear, and explanations range from catastrophic events, such as neutron star mergers, to exotic possibilities such as signals from alien civilizations. Each newly discovered outburst raises more questions than it answers, making the FRB one of the most exciting areas of modern astronomical research. Finally, we face the mystery of the WOW signal. Discovered in 1977, this one-time radio signal appears to come from the direction of the constellation Sagittarius. Despite extensive searches, no similar signals have been detected since, prompting scientists to speculate about its origin. Was this a natural cosmic event? Or is it a signal from other intelligent life in the universe? The ongoing study of these phenomena reflects our desire to deepen our understanding of the universe and our place in it. Galaxies exhibiting unusual behavior provide an interesting contrast to their typical counterparts. Consider, for example, the phenomenon of exploding star galaxies. Unlike ordinary galaxies, where stars form slowly and at a constant rate, interstellar galaxies undergo intense star formation, often many times the rate of star formation in the Milky Way. This rapid star formation is often caused by interactions with other galaxies or the environment. This causes an increase in the density of gas and dust that feeds the new stars. Another interesting example is the green bean, a class of galaxies characterized by a bright green color due to the release of oxygen and other elements during active star formation. These small, compact galaxies challenge conventional ideas about size and mass in galaxy evolution. Unlike large spiral or elliptical galaxies, green beans may have relatively little mass, but can be incredibly efficient at producing new stars. This unusual behavior raises important questions about the conditions necessary for star formation and the life cycle of galaxies. The implications of studying these unconventional galaxies are more than curious. By studying their unique properties, astronomers can learn about the processes that govern the formation and evolution of galaxies. For example, The role of mergers and interactions may help us better understand how galaxies grow and evolve in space-time. The prevalence of such unusual features may indicate that what we consider typical may represent just a snapshot of a larger dynamical process. By unraveling the mysteries of these atypical galaxies, scientists are not only improving our understanding of galaxy evolution, but also exploring the fundamental physics underlying the cosmos. Each discovery expands our understanding of the different forms of order in the universe, and ultimately enriches our understanding of how galaxies, including our own, formed. Planets that challenge established scientific models often force researchers to rethink the basic principles of planet formation. For example, the discovery of gas giants in orbits very close to their parent stars has led to a re-evaluation of how worlds of this scale form in such a hostile environment. According to conventional theories, gas giants should be located far enough away from their stars to accumulate the large amounts of gas needed to form them. However, the existence of so-called hot Jupiters raises questions about the mechanisms by which such formations can occur. It's also led to the discovery of planets of unusual composition, very large on Earth, but smaller than the gas giants. Paradox: some of these planets appear to be composed of materials that do not fit into existing categories, prompting researchers to propose new models of formation. These models can account for the concept of planetesimals, small particles of matter that stuck together in the early stages of planet formation under different environmental scenarios. Understanding how these unique planets formed allows scientists to create versatile and adaptive models. In addition, advances in astronomical technology have allowed researchers to discover exoplanets of various sizes and compositions, the behavior of many of which does not match the behavior observed in our solar system. For example, planets that exhibit extreme atmospheric or weather conditions raise new questions about how a planet's atmosphere is formed. Factors such as stellar radiation, gravitational effects, and chemical processes must be taken into account, leading to innovative theories that push the boundaries of our knowledge. Such unexpected planetary discoveries not only enrich our understanding of the universe, but also demonstrate the adaptive nature of scientific research. Each anomalous discovery is a reminder that our models are not carved in stone, but must evolve in response to new data. This dynamism is at the heart of scientific progress, as it unlocks the mysteries of planetary formation and function, ultimately bringing us closer to a deeper understanding of the cosmos. Among the most mysterious cosmic objects in the universe are black holes, quasars, and dark matter. Each of these phenomena has caused intrigue and mystery in the scientific community, and their enigmatic nature raises difficult questions about the structure of our universe. Black holes, for example, have such a strong gravitational pull in space that even light cannot escape them. The black holes predicted by Albert Einstein's general theory of relativity come in a variety of sizes, from interstellar black holes formed by the collapse of massive stars to supermassive black holes at the centers of galaxies. Their origin remains a mystery, as the processes and evolutionary mechanisms leading to their formation are still unclear. Researchers continue to address questions about how supermassive black holes form and grow to their size. Quasars, or quasi-stellar objects, represent another astrophysical mystery. These incredibly bright objects, which create supermassive black holes at the centers of distant galaxies, emit enormous amounts of energy that engulf entire galaxies. The existence of quasars requires explanations regarding the early universe and the formation of galaxies. Although quasars are believed to have played an important role during the cosmic dawn of the universe several billion years ago, details about how these energy centers evolved and affected galaxies remain elusive. There is also dark matter, which is believed to make up about 27% of the total mass of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, but only detects it through its invisible and gravitational properties. The main mystery surrounding dark matter is figuring out what it is. Several theories have proposed different candidates for the role of this mysterious substance, but no direct detection has been achieved, leading to an intriguing mystery beyond our understanding of physics. These cosmic mysteries challenge our understanding of reality and drive scientists to delve deeper into the cosmos. As new technologies and techniques develop, this research may one day unlock the secrets of these fascinating celestial phenomena, changing our universe and our place in it. The universe is a mysterious place, and our understanding often struggles with phenomena that don't fit into existing frameworks. Dark matter and dark energy are two such concepts that complicate our understanding of cosmology. Although we can fully observe galaxies, stars, and planets, much of the universe remains hidden from direct detection, leading scientists to believe that most of the universe is made up of these entities. Dark matter makes up about 27% of the universe. It does not emit, absorb, or reflect light, making it invisible to our modern devices. However, the existence of matter is evident from its gravitational influence. For example, galaxies spin at such high speeds that if only visible matter existed, they would disintegrate, and they are stuck together by this invisible mass. This discovery raises profound questions about the nature of the cosmos, as the fundamental components of our universe are completely undetectable by conventional methods. There is also dark energy, which makes up 73% of the universe. This mysterious force acts as a kind of anti-gravity, causing space to accelerate. The discovery of dark energy in the late 20th century forced scientists to rethink their understanding of the fate of the universe. If this trend continues, the universe could eventually become a cold, dark space. The existence of dark energy not only complicates our models, but also raises philosophical dilemmas about the ultimate fate of what we know. The interaction of dark matter and dark energy is forcing scientists to rethink the basic principles of physics and cosmology. It initiated ongoing research that combined observation with theoretical physics, raising new questions about the nature of reality. As we delve deeper into these topics, we come closer to unraveling the mysteries of the cosmos, while much of the universe remains a deep mystery. The idea that nothing in the universe exists has puzzled scientists for decades, and recent discoveries continue to deepen the mystery. Astronomers have long known that the matter consisting of stars, planets, and galaxies makes up only a small fraction of the total mass needed to explain the gravitational effects of the universe. Much of it, called dark matter, raises questions about what it is actually made of. One of the exciting discoveries is the study of galaxy clusters with modern observations using synchronized radio arrays. These observations have revealed large cold clouds of gas at the beginning of the universe. This gas makes up an important part of the universe's baryonic matter, but until now, it has gone largely undetected. Its existence indicates that ordinary matter is not all we see. Instead, these discoveries suggest that additional, undiscovered forms of matter may be lurking in the cosmic shadow. In addition, using innovative techniques such as gravitational lensing, scientists have been able to detect how light bends around massive objects, giving us a glimpse of invisible mass. This lensing technique has provided a more accurate picture of the distribution of matter in galaxies, showing that missing matter is not just a defect, but a sign of more complex structure in the core of the cosmos. Another area of interest is the study of the cosmic microwave background, the residual radiation after the Big Bang. Through precise measurements, scientists have detected changes in the background radiation that indicate that the mass and energy content of the universe is much higher than what can be directly observed. This discovery supports the theory that the universe is filled with forms of matter we don't yet understand, and heralds the discovery of new physics. Scientists are determined to solve these complex mysteries in search of evidence that can close the gap in understanding the true composition of the universe. The study of extreme conditions in space can indeed shed light on cosmic anomalies, opening the door to understanding the universe's most fascinating mysteries. In environments such as the icy satellites of Jupiter or the warm surfaces of planets such as Venus, conditions now exist that push the boundaries of our knowledge in physics, chemistry, and biology. How matter behaves under extreme pressure, temperature, or radiation can provide insights into phenomena that are still poorly understood. Take, for example, the icy crust of Europa, one of Jupiter's satellites. Beneath this frozen crust is a vast ocean of liquid water that could support life. Studying such environments not only helps scientists unlock the potential for extraterrestrial life, but also allows them to find links to dark matter and dark energy. These elements play an important role in the behavior of galaxies and the expansion of the universe, suggesting a deep connection between the behavior of matter under extreme conditions and the fundamental structure of the cosmos. By studying Saturn's powerful radiation belts, scientists have observed their effects on robotic and human-powered spacecraft. These observations allow us to better understand the role of radiation in space, as well as to understand cosmic rays and their origins. In addition, the gases in the atmospheres of the gas giants reveal information about the chemical reactions that occur under pressure, helping to piece together the mystery of the evolution of certain cosmic structures over time. Each mission to these extreme environments serves as a springboard for deciphering the cosmic anomalies we observe, such as the uneven distribution of galaxies or the unexplained acceleration of the expansion of the universe. By studying extreme conditions in space, we not only observe the workings of our solar system, but also understand the fundamental processes that govern the universe. These studies thus serve as an important thread in the fabric of our understanding, uniting knowledge of the visible and invisible aspects of reality. Theoretical physicists serve as architects of our understanding of the universe, developing schemes to explain unknown and natural phenomena. Their work often begins with observations of unexplained or mysterious behavior in the universe, such as the enigmatic composition of dark matter or the special acceleration of distant galaxies. By formulating hypotheses and creating mathematical models, they generate potential explanations for these mysteries, turning abstract ideas into theories that can be systematically tested. One of the main tools at their disposal is mathematical modeling, which allows scientists to simulate conditions and outcomes based on their theories. For example, they can predict the behavior of particles at very high energies, something that does not exist on Earth but can be studied directly through experiments like particle gas pedals. These mathematical frameworks guide experiments and observations and give researchers a goal to strive for, thereby bridging the gap between theory and empirical data. In addition, theoretical physicists often seek to combine different sections of physics to achieve a more complete understanding of the fundamental forces of nature. A perfect example of this combination is line theory, in which all particles are not point-like, but lines of tiny vibrations. This approach reconciles quantum mechanics with the general theory of relativity, effectively eliminating some of the contradictions observed at cosmic scales. By proposing such ambitious theories, physicists provide a broader context that can ultimately provide explanations for seemingly inexplicable phenomena. In conducting research, theoretical physicists often collaborate with experimental physicists who collect data to confirm or refute theoretical predictions. This interplay between theory and experiment forms a dynamic cycle of understanding that drives scientific progress. The mysteries of the universe are not just obstacles, they are invitations to explore. By doing so, we expand the frontiers of human knowledge and increase interest in the fundamental nature of reality. Some cosmic phenomena contradict our current understanding of physical laws, and this resistance is often due to the complexity of the universe. The laws of physics as formulated work remarkably well under conditions we can observe and experience. In deep space or extreme environments, however, the same laws may produce unexpected results or prove insufficient to explain what we see. Black holes, for example, present a serious mystery. According to the general theory of relativity, nothing can escape the gravitational pull of a black hole, not even light. However, the discovery of phenomena such as Hawking beams suggests that black holes can emit radiation and eventually vaporize. Realizing this forces physicists to reconcile quantum mechanics with the general theory of relativity, pushes the boundaries of the theoretical framework, and shows that our current models are incomplete. In addition, the accelerated expansion of the universe observed through distant supernovae indicates the presence of dark energy, a mysterious force that makes up about 70% of the universe. The nature of dark energy remains unknown, and although it is consistent with our observations, it challenges our traditional understanding of gravitational behavior and dynamics. This discrepancy with expected results is forcing scientists to rethink the structure of spatial understanding. The existence of phenomena such as gamma-ray bursts or the mysterious behavior of pulses shows the limitations of our models. Each of these observations is a reminder that science is a constantly evolving field. As data accumulate and technology improves, we will be able to discover deeper truths about the cosmos. And our current laws are not the last word, but stepping stones to a fuller understanding of the mysteries of the universe. The discovery of cosmic phenomena that challenge our current scientific models opens the door to deeper questions and a realm of potential discoveries. Every time astronomers observe something that does not fit existing theories, it tells scientists that there may be new aspects of the universe that have not yet been explored. Such a scenario is not only intellectually exciting, but also forces scientists to expand or even revolutionize our understanding of physics and astronomy. Take, for example, the unpredictable behavior of dark matter and dark energy. For decades, these mysterious components of the universe have shaped our understanding of cosmic expansion and structure formation. If new observations reveal phenomena that cannot be explained by existing theories, researchers may reconsider the nature of gravity or consider the action of entirely new forces. This can lead to extensive research that requires interdisciplinary collaboration between physicists, astronomers, and mathematicians to create new theories based on this research. Moreover, such discoveries may have cascading implications for technology and practical applications. Advances in space-observing technologies often arise from these challenges, expanding the capabilities of instruments. Innovations in data analysis, sensor design, and even computing power will come in handy when trying to understand these anomalies. For example, the study of gravitational waves has led to new methods and technologies that have benefited a wide variety of fields, from medical monitoring to telecommunications. Finally, the implications are both philosophical and scientific. Encountering cosmic phenomena that defy explanation forces us to rethink our understanding of reality. This ignites the spirit of exploration, reminds us of the limitations of our knowledge, and creates a humble attitude. The quest to understand the universe never stops, reflecting our shared journey to unlock the mysteries of our existence. With each anomaly discovered, there is always something new for us to learn, explore, and discover new mysteries. Wormholes are interesting theoretical constructs in astrophysics, often described as shortcuts through the fabric of space and time. Imagine a large two-dimensional piece of paper depicting the universe. You can imagine how a wormhole would work, if you touched this leaf at 2 points and created a direct connection between them. In essence, it connects two distant regions, potentially allowing travel between them. The concept of wormholes comes from Einstein's general theory of relativity, which suggests that mass and energy can change over time. Although the general theory of relativity allows for the existence of such space tunnels, there is still no conclusive evidence that they actually exist. Scientists believe that wormholes can be formed from exotic substances with negative energy density that have not yet been found in nature. This exotic substance is needed to stabilize the wormholes so they don't collapse before passing through them. In the broader context of space travel, the idea of using worms opens up interesting possibilities. If they do exist, and we can find a way to control them, interstellar travel, which takes thousands of years, could theoretically be reduced to a few moments. The concept captures the imagination and raises questions about future research, communication, and even the nature of time itself. However, for all their appeal, wormholes are still in the realm of theory. Scientists continue to study the laws of physics to find out how they translate into practical reality. Ongoing research emphasizes the dynamic nature of our understanding of the universe. As our knowledge of physics grows, possibilities such as worms and what they might mean for humanity's place among the stars are being discussed. Multidimensional theories, especially solid theory, have captured the imagination of scientists trying to unravel the mysteries of the universe. These theories suggest that there are additional dimensions besides the usual 3 dimensions of space and 1 dimension of time. Some theories suggest 10 or 11 dimensions that could explain anomalies that have long puzzled physicists, such as the behavior of gravity on a cosmological scale or the properties of subatomic particles. For example, one interesting anomaly is the nature of dark matter and dark energy, which together make up 95% of the mass energy of the universe, but are largely excluded. Multidimensional theories can provide a framework in which these mysterious entities interact in different ways, as we understand them. They suggest that what we perceive in our limited 4-dimensional system is a shadow of more complex interactions existing in larger dimensions. However, these universal models are fraught with serious problems. One major obstacle is that they often operate at energy scales beyond those that can be tested with current or new technologies. The Large Hadron Collider, for example, can reach a certain energy level and not explore additional dimensions where these phenomena may occur. Without experimental data to confirm or refute these theories, they remain largely mathematical constructs. Another problem is conceptual rather than technical. Traditional physics relies on an intuitive understanding of the 4 dimensions we encounter every day. Incorporating additional dimensions often leads to unintended consequences or rationalizations. In addition, the complex math used in formulating these theories can be difficult, hindering the spread of these ideas and increasing public understanding. Despite these problems, the exploration of multiple theories is a testament to humanity's ongoing quest for knowledge. As scientists delve into the depths of the mysteries of the universe in search of a unified understanding of the cosmos, consider the idea of a multiverse, which suggests that our universe may not be the only universe, but only one of many. This concept changes our understanding of what makes the universe unique. If there are other universes with unique characteristics, physical laws, and histories, this shifts the focus from viewing our universe as a whole to viewing it as part of a larger ensemble of reality. One of the interesting aspects of multiple theories is that they open the door to possibilities we cannot imagine. Imagine a universe in which the basic constants of nature are slightly different, possibly allowing for the existence of life forms that we cannot even imagine. This concept creates a broader landscape of reality that diminishes the importance we previously placed on Earth as the sole cradle of life and existence. Instead, Each universe may represent different results of the same basic questions we are trying to answer in our own reality. Moreover, the concept of diversity forces us to rethink the nature of scientific inquiry. In trying to understand our universe, scientists often assume that it is unique. If there are multiple universes with different laws of physics, it suggests that our understanding may be superficial. It assumes that our scientific observations are limited and shaped by the specific conditions and laws that exist in our universe. The implications of different theories extend further into the philosophical realm. They challenge concepts of existence, probability, and the nature of reality. When we think about these possibilities, we begin to appreciate the complexity and interconnectedness of life on a cosmic scale. Exploring how the multiverse changes our understanding forces us to think more deeply about our place in the universe and define what it means to be unique. Our understanding of the universe is based on many theories and principles, but the possibility of unknown forces adds another fascinating mystery. The modern system of physics relies on four fundamental forces: gravity, electromagnetism, weak nuclear interaction, and strong nuclear interaction. However, the pursuit of knowledge often raises more questions than answers, prompting scientists to investigate whether additional forces could be influencing our universe. One important piece of evidence for the existence of unknown forces is phenomena such as dark matter and dark energy. Observations show that visible matter, such as stars and galaxies, is only a small fraction of the total mass and energy of the universe. Dark matter, which does not emit, absorb, or reflect light, has a gravitational effect, but its exact nature remains unknown. Dark energy appears to be the force accelerating the expansion of the universe. This suggests that the characteristics of entities may go beyond the four known forces or interactions. Moreover, experiments in particle physics provide good reasons to consider additional forces. In particular, high-energy collisions at facilities such as the Large Hadron Collider can reveal unexpected particles or interactions that may indicate new force dynamics. The discovery of the Higgs boson was a major milestone, but the data are being analyzed for anomalous behavior or deviations from the predictions of the Standard Model. Such disturbances may represent phenomena that cannot be fully explained by current theories. The search for unexplained forces is also attracting attention in cosmological studies, the order of galaxies, and the large-scale structure of the universe. If the gravitational equations do not explain some of the motions observed in the rotation of galaxies, there may be a force that we have not yet identified. Thus, while concrete evidence for the existence of undiscovered forces remains elusive, research in astrophysics and particle physics is continually opening new avenues for understanding the fundamental complexity of the universe. Imagine a powerful force that can shape entire galaxies but is hidden from view. A vision of light and a warping of time that try to escape us. It is a reality of a supermassive black hole lurking at the center of countless galaxies, including our own. But the story does not end there. Recent discoveries have proven that these space giants are not just passive consumers of matter. They influence the structure of the universe, play an important role in the formation of stars, shaping the evolution of galaxies, and even the creation of planets like Earth. Today, we delve into the hidden mechanisms behind these forces and explore the revolutionary changes that ultimately reveal these mysteries. What we discover could change our view of the universe forever. First, let's talk a little theory, making sure we're on the same page. Let's start with quasars, which serve as the energetic hearts of active galaxies in the universe. Powered by supermassive black holes, these bright beacons radiate the collective light of all the stars in the galaxies. In our case, a subset of quasars called red quasars has attracted the attention of astronomers. Unlike their blue counterparts, red quasars are covered in cosmic dust, which plays a key role in their unique properties. The observed reddening of quasars is a direct effect of the dust surrounding them. Dust absorbs short, blue wavelengths and lets in longer, red wavelengths. This phenomenon not only changes their appearance, but also enhances their radio emission, as recent studies using data from the Dark Energy Spectroscopic Instrument, or DESI, and the Low-Frequency Array LOFAR have shown. Victoria Fackett and her team at the University of Newcastle found that red quasars emit stronger radio signals than their dust-free blue counterparts. Powerful radiation streams from the quasar collide with the dust, exciting the molecules inside and causing them to emit radio waves. This interaction is key to understanding why red quasars are stronger in radio air. But why are these red quasars so important? The answer lies in their age and stage of evolution. Red quasars are thought to represent the young stage of the life cycle of active galaxies. The dust covering them is not just an obstruction, but a remnant of the galaxy's past, likely formed during star formation, the period of violent stars formed by galactic mergers or other dramatic interactions. As the supermassive black hole continues to feed, its currents slowly shake off this veil of dust, revealing a blue quasar with radio emission in its place. This explosion phase refers to the evolution of a quasar from a dusty, radio-intense form into a blue quasar with purged, quenched radioactivity. Observing red quasars gives astronomers insight into the early stages of this transformation and provides valuable information about the mechanisms that govern the evolution of galaxies. The discovery of thousands of red quasars by Fawcett's team underscores their importance in the cosmic landscape. These objects are not just rare anomalies, but important pieces of the puzzle for understanding the evolution of galaxies. As supermassive black holes grow and expand, so do their galaxies, and the activity of quasars plays a key role in this dynamic process. Now that we understand the basics, we can continue our journey and delve deeper into the explosion phase and its impact on the evolution of galaxies. The explosion phase theory provides a deeper understanding of the life cycle of red quasars in the centers of young active galaxies. This stage represents a critical period of evolution, when the supermassive black hole at the center begins to purge itself of dense clouds of gas and dust. And this turns the galaxy from a red quasar to a blue one. At the heart of this theory is the enormous force created by the supermassive black hole, which is powered by the material of the accretion disk. The intense gravity within the disk creates friction, heating the gas and dust to millions of degrees. This advance not only illuminates the quasar, but also releases energy that leads to the explosion phase. Consisting of high-speed winds and magnetized jets, these jets act like cosmic brooms, sweeping away dust and gas. As these jets collide with the material, they create shock waves that further accelerate the cleaning process. Over time, this cleaning opens up the interior of the quasar, reducing the amount of dust and allowing the quasar to shine brighter in optical and ultraviolet wavelengths, a phase we now call a blue quasar. This theory is supported by observations made by space telescopes. JWST's infrared capabilities allow astronomers to penetrate the dust and obtain detailed images and data that reveal the dynamics of this explosive phase. In particular, these observations reveal interactions between quasar jets and surrounding matter, consistent with the process of ejecting dust and gas from the galactic center. These results are in good agreement with the predictions of the burst phase theory and indicate that red quasars are indeed in a transition state. Now, as an example, let's turn to the news itself. Several times, and we go again, the James Webb Telescope has opened a new chapter in our understanding of space. Among the many discoveries, the case of the galaxy ESO428G14 stands out. Located about 70 million light-years away, an active galactic nucleus, or AGN, is a region centered on a supermassive black hole that exerts a powerful influence on its surroundings. ESO428G14 is not just any galaxy. An AGN is a powerful radiation source covering the entire electromagnetic spectrum, caused by a supermassive black hole absorbing matter at extraordinary speeds. This phenomenon creates a large amount of energy, making active galactic nuclei one of the most luminous objects in the universe. But what has attracted astronomers' attention is the recent discovery of shock elements in the clouds of dust and gas surrounding the black hole, which have complicated our understanding of how these cosmic giants interact with their surroundings. Most theories assumed that the energy heating the surrounding dust in the AGN came directly from the supermassive black hole. However, the JWST observations revealed something even more interesting. The energy heating the dust comes not only from the intense radiation of the black hole, as well as from strong interactions with jets of gas ejected from the black hole's columns at the speed of light. These jets collide with the surrounding matter in what astronomers now call shock waves. These influencers were a revelation. Previously, scientists debated how active galactic nuclei transfer energy to their surroundings. It was surprising that radio jets could cause so much damage to nearby dust and gas. The discovery challenges long-standing assumptions and opens new questions about the dynamics of supermassive black holes. The implications of these findings are profound. By detecting the interaction between radio jets and surrounding matter, JWST is revealing how supermassive black holes affect not only their surroundings, but the entire galaxy. Once thought to be a simple byproduct of black hole activity, these jets now appear to play an important role in shaping the environment, influencing the rate of star formation and the overall structure of the galaxy. This phase is an important element in the complex interactions between supermassive black holes and their galaxies. To better understand the effect of active galactic nuclei on the surrounding space, let us study the feedback mechanisms that regulate the interaction between supermassive black holes and their cosmic neighbors. It has long been known that at the center of many galaxies, there is a supermassive black hole, also known as an AGN, surrounded by a dynamic and turbulent environment. An AGN is a region of strong energy fluxes driven by strong radiation and an accretion disk, the giant structure of gas and dust that feeds a black hole. This disk, heated to millions of degrees by its immense gravity, emits radiation across the entire electromagnetic spectrum, from X-rays to radio waves. The accretion drive is not a uniform structure. It has distinct regions that behave differently depending on its proximity to the black hole. In the inner regions, matter rotates at incredible speeds, generating enormous amounts of heat and emitting high-energy radiation. But recent observations have provided new insights into the outer edges of these disks. For the first time, astronomers have observed the outer edge of the accretion disk, providing a more accurate picture of its size and structure. Using the James Webb Space Telescope and infrared spectrograph by Young, the researchers detected emission lines in the infrared spectrum from the distant quasar 3Z002. These lines, broadened by the Doppler effect, show the size of the accretion disk, confirming its width and the turbulent conditions within it. The authors of the study hypothesized that these emission lines occur when atoms in the disk absorb energy, enter an excited state, and eventually return to a lower energy state, emitting light. The unique double profile of these lines, due to the rotation of the disk, allowed astronomers to measure the size of the disk and helped to understand the behavior of matter in the influence of the supermassive black hole. The accretion drive, is not the only actor. At the AGN theater, radio jets shoot out from the accretion disk's poles, streams of charged particles accelerated to the speed of light by the black hole's magnetic fields. These jets are not just products, but powerful forces that shape the environment around the active galactic nucleus. Colliding with the surrounding dust and gas, they generate massive shock waves that affect the evolution of the entire galaxy. The interaction of these jets with the interstellar medium can cause star formation in some regions and collapse in others. This feedback mechanism, known as AGN feedback, plays an important role in regulating galaxy growth. By enriching or stripping the surrounding gas of heavy elements, these jets can dictate the rate of galaxy growth, effectively controlling the balance between star birth and death. In addition to jets, black holes exert their effects through tidal disruption events, or TDEs, when a star comes too close to a black hole and is pulled apart by gravity. This process, called spaghettification, causes the star to stretch and collapse, with some material falling into the black hole and the rest being ejected into space. Recent studies have confirmed that not all of the star's material is absorbed by the black hole. Instead, most of the gas escapes, forming a large spherical cloud that can mask high-energy radiation such as X-rays. Detected using polarized light, this cloud provides insight into the effects of TDE when the black hole's appetite leaves a visible trail around it. But this dust is not just tiny particles floating in a vacuum. It plays an important role in shaping our understanding of the universe and contains fundamental information about the processes that govern the cosmos. Cosmic dust, often thought of as simple space debris, plays an important role in complex processes in the universe. Cosmic dust is formed mainly from stellar debris and consists of micron-sized particles, the size of a human hair, and elements such as carbon, silicon, and metals. These particles are killed not only by the phenomena discussed above, but also by various interstellar events such as supernova explosions, when stars eject their outer layers into space, or by the gentle pulverization of matter by red giants. The formation of cosmic dust is evidence of the life cycle of stars. In the case of a supernova, a powerful explosion scatters heavy elements into space, which eventually cool into dust grains. Thus, as red giants expand and lose their outer layers, they slowly expel material between stars, contributing to the formation of cosmic dust. This dust can later be incorporated into new stars, planets, and even life, making it an essential component of space processing. But cosmic dust is not only a product of stellar evolution. This has profound implications for how we observe the universe. One of the most serious problems caused by dust is its ability to obscure our view of celestial objects. Dust particles can scatter and absorb light, especially in the visible spectrum, making it difficult to see through dense clouds around galactic centers, or active galactic nuclei. This obscurity is especially problematic when studying black holes and quasars, where the presence of dust can obscure the most interesting features. However, as we mentioned above, JWST's advanced infrared capabilities allow it to penetrate the visible range of the spectrum. Through infrared observations, JWST will be able to detect heat emitted by dust particles, as well as light from objects hidden behind or within clouds. As we continue to unravel the mysteries of space, the future looks even more promising with the Nancy Grace Roman Space Telescope. It will be launched in 2027 and will complement JWST by taking infrared images that are 200 times larger than Hubble, but with the same level of detail, offering a wide panoramic view of the universe. The novel's extensive field of vision will allow him to collect an unprecedented amount of data, providing information on billions of galaxies and helping to create a three-dimensional model of the universe. This telescope will not only expand our understanding of cosmic dust and its role in galaxy formation, but may also answer some of the big questions in astrophysics, such as the nature of dark energy and the structure of the universe on the largest scale. Whether it's mapping the expansion of the universe or discovering a new exoplanet, the future of space exploration holds endless possibilities. Thanks to revolutionary technologies, we are on the verge of unlocking secrets that will change the way we think about space. Be curious, because the universe is full of mysteries waiting to be discovered. At one point in our lives, we wondered if we were alone in the universe. With so many planets orbiting multiple stars in our own or other distant galaxies, why haven't we encountered signs of extraterrestrial life yet? But what if evolved alien life forms survive and hide? A dark front, SATI hypothesis, that technologically advanced civilizations may have developed outside the solar system. But they are not going to make contact because they fear attacks from other civilizations, or they are preparing for an attack. Today, you will learn about the dark forest theory and why you should avoid anyone who can hear you in the vast space. 1. The dark forest hypothesis. Author and primary source. The author of the dark forest hypothesis, DFH, is science fiction writer Liu Cixin. It should be noted that this is not a scientific theory, and it is not based on any concrete evidence. In 2008, Liu Cixin published his best-selling science fiction novel. The dark forest theory is presented for the first time in this book. The essence of the theory is that each spatial civilization seeks to obtain the resources necessary for its continuation. Thus, life on Earth is hidden to prevent another civilization from being destroyed, to attack and ensure its survival. So why is this theory called the dark forest hypothesis? In his novel, Liu Cixin compares a dangerous existence to a forest inhabited only by hunters. The author describes the civilizations as metaphorical armed men in the dark forest, who advance silently for fear of being discovered by hunters. If one hunter can detect the other, he attacks first before his opponent does the same. With this in mind, there are several ideas that promote DFH. The first is that there are hypothetical alien civilizations. They hide because of the threat of attacking others and losing resources such as living planets. Within the Black Forest hypothesis, the foundation of every civilization is known as the chain of suspicion. This phenomenon is caused by a lack of communication, which directly leads to mistrust. A second idea is that a civilization that actively transmits radio signals and gives away its space can be invaded or destroyed by others for resources. A third concept is that communication is rare in this type of system because each civilization seeks to survive, primarily through expansion. However, an agreement is possible if its terms are beneficial to both civilizations. Liu Cixin portrays the universe as a battleground for limited resources, where alliances are almost impossible. Finally, in Liu Cixin's hypothesis, hunter-gatherers are similar to high-tech civilizations. Therefore, if a civilization is not advanced enough to show itself in space, it will be ignored or become an easy victim. 2DFH is the answer to Fermi's paradox. As you know, in 1950, the famous physicist Enrico Fermi, while discussing the flying saucer with his colleagues, suddenly asked, "Where is everyone?" referring to extraterrestrial life examples that illustrate the origin of the famous Fermi paradox. We talked about it at length in this video on our channel. Fermi, if our galaxy was formed several million years before the birth of humanity, other civilizations much older than Earthlings may have arisen during this period. This means that the Milky Way galaxy should be full of civilizations that can receive our signals due to our technological advancements, as well as travel across the galaxy. However, so far, we have seen no sign of alien activity. Why are they on Earth and not approaching our planet? Determine the number of extraterrestrial civilizations within our galaxy. The famous Drake equation was derived in 1961, but we cannot use it to explain why aliens leave no signs of life. Therefore, at this point, there is only a theoretical explanation for the Fermi paradox. Furthermore, according to physics professor Adam Frank, the probability that Earthlings are the only civilization in the universe is very low. 1 in 10 billion trillion, or 10 to 22 powers. The professor suggests that our evolution is not unique, and that other civilizations may have preceded us or been much longer than us. There are more than 70 hypothetical solutions to this question, one of which is the Black Forest hypothesis. Of course, we cannot test the validity of DFH due to current technological limitations, but Liu Cixing's theory provides a logical explanation for why we have yet to receive any alien signals or find signs of life on other planets. It is dangerous for other civilizations to give up their land for fear of invasion. Although this hypothesis presents very clearly defined ideas, there are some inaccuracies in DTH. For example, if there are other civilizations, they must differ from ours because of different degrees of gestation, Fermi noted. This means that there may be civilizations at or above our technological level that actively seek out alien life or explore their own systems like we do because they don't see it as a threat. So we are not just signalers, because civilizations don't grow out of fear of discovery if they don't face opposition. Third, more about the assumptions of the Dark Forest hypothesis. The idea of conquering other territories and destroying the first civilization on a cosmic scale is reminiscent of our historical experience on Earth, namely colonization and war. There are many reasons why people conquer other nations. However, in most cases, such as during the European colonization of Africa in the 19th century, the main motive was land and natural resources. The rapid growth of industry in Europe required resources available elsewhere on the continent. Thus, the colonization of Africa helped the development of European countries, but the African land and its people suffered from this expansion. DFH presents the same colonial model as the reason for one civilization attacking another. We are still looking to expand for the continued existence of humanity, explore exoplanets and other star systems, and plan to colonize Mars. The red planet is also rich in natural resources for technological development. So, assuming that other civilizations have similar goals, we may have to fight for lands that can serve humanity. Otherwise, our survival would be in danger because, according to this hypothesis, survival and the necessary resources are essential to the preservation of the species. Besides the need to replenish a limited resource, there are other reasons for the aggressive behavior of civilizations. For example, as we discussed earlier, DFH introduces a concept called chain of doubt. This concept is closely related to another aspect of this hypothesis called technological explosion. The essence of the chain of suspicion is that civilizations cannot know whether others are benevolent or hostile. These doubts can lead to preemptive attacks and self-defense. According to researcher Chao Yu, this chain can only exist among civilizations with a high level of technological development, because they can objectively assess their own and others' capabilities. Thus, if there is a large difference in their development levels, a chain does not form. Technological explosion describes the ability of space civilizations to make rapid scientific and technological leaps. Powerful new hunter may pose a threat to others because advanced civilizations may fear it or seek to destroy it. However, Chao Yu notes that any attack can also infect the attacker, as other civilizations with similar or higher levels of development can detect it, thus creating a chain of suspicion. However, despite the obvious advantage in attacking other civilizations and hideouts, the DFH is considering another scenario. kindness. The purpose of the bounty is to refrain from attacking other civilizations that, even if detected, are unlikely to be able to respond to the signal. In the dark forest, this tactic is dangerous because it reinforces the chain of suspicion. Another civilization identified with a benevolent civilization is aggressive or rapidly growing, so he can destroy others in the future and live by collecting enough resources, while the benevolent civilization will be destroyed. If we think that extraterrestrial life exists and it's far ahead of us, it might attack us because it's a survival tactic with the highest chance of success. This is not good news. So, other than an invasion of our planet, are there any viable options for Earth based on the dark forest hypothesis? Let's look at this from a game theory perspective. Number 4. Game theory and DFH. The main goal of game theory is to study how people make decisions based on certain circumstances in order to achieve the best possible outcome. Imagine that Earth is a civilization and advanced alien life is a civilization. B received the radio signal. Now B has 3 strategies. Attack, don't be obvious, but be suspicious, or respond in the hope of friendship. Even if A fights back, attacking will be considered the most favorable strategy. On the other hand, according to researcher Alina Su, this scenario could be a loss for B if Planet B could send a signal to transfer its coordinates to other civilizations. Perhaps the best option in this case would have been to remain unclear. If both civilizations do nothing, good will not work either. On the one hand, it will put A and B out of danger, and on the other hand, they will not be able to get the resources they need. There is also an opportunity to become friends. If 2 civilizations agree to an alliance, one of them will gain advantages such as the ability to use foreign technology. Other civilizations that offer friendship will also benefit, albeit to a lesser extent. Does this alliance mean the best-case scenario for both civilizations? Maybe, but it comes with some pitfalls. First, kindness, as you know, is very dangerous because hypothetically extraterrestrial civilizations are not likely to be friendly very often. Second, the amount of available resources, even in the case of a trade agreement, is less than that obtained by force. Thus, the probability of a theoretical attack on Earth is the highest, but this course of events could seriously damage the attacker. However, other civilizations may fear Earth's unknown military potential. So, choose stealth or friendly tactics. 5. Does the risk of sending a signal into space mean that we should avoid sending a signal into space if the probability of a ground attack is higher than the other options? According to the DFH, messages to other civilizations could threaten our security. This is the same idea as PYY many astrophysicists, including Stephen Hawking. Since the breakthrough in space exploration in the middle of the last century, scientists have shown great interest in the search for alien civilizations. In 1974, the famous Arecibo message was sent to a star cluster 21,000 light-years away. Since then, several radio messages have been sent into space, the most recent of which dates back to 2017. Physicist Stephen Hawking believes these messages could lead to the scenario described in the dark forest. According to him, the arrival of an alien civilization on Earth could have the same consequences for us as the colonization of America in the 15th century. Therefore, he believes that this type of communication should be stopped. However, other scientists, including SETI astrobiologist Douglas Vakoch, believe that fear of sending messages could lead to Earth's isolation. In addition, Vakoch noted that alien civilizations could invade our planet while it was still developing, so we should not be afraid to hear about extraterrestrial life. Finally, the dark forest hypothesis also promotes the idea of differences in hunter-gatherer behavior. That is, all civilizations will not attack us if they find our signal We travel into space to make discoveries and look beyond reality itself. What if the cosmos is invisible in all its glory? Could it be that our universe is an illusion, a complex facade covered by the complex laws of physics? Our quest leads us into a labyrinth of time, moving endlessly through the universe. Time stretches, compresses, and binds all aspects of existence. It acts as an invisible link, connecting the past, the present, and the uncertain future, forming the foundation of our reality. As our journey reaches its climax, we will encounter two formidable pillars of understanding: the speed of light and the mysterious force of gravity. The speed of light, the boundary that separates the possible from the impossible, and gravity, the invisible force that represents the interaction between all matter, bending the fabric of space and time. Through them, we will try to decipher the cosmic code that governs the universe. Fasten your seatbelts for an unknown space journey, where we challenge our understanding of the universe based on the principles of time, light, and gravity. Everything around us, even ourselves, is part of our universe. We are used to thinking of it as something ephemeral, but what is the universe? Today, we're going to challenge what you know about the universe. What if everything we see and feel is an illusion? Hold on, because we're about to delve into the mysteries of the universe. First, let's look at what we know about the universe. For scientists, the paradox of how our universe was formed is still a mystery. As we know, 13.8 billion years ago, according to the Big Bang theory, the universe was formed from a singularity where all the fundamental forces converged. On the other hand, according to the Hawking-Hartle theory, the universe did not originate from a single point. It existed as pure space without time, with the Big Bang coming later. Despite the diversity of current ideas about the origin of the universe, cosmic inflation began at some point. Protons and neutrons formed in microseconds, forming basic building blocks like hydrogen and helium. Then, after cooling, 360,000 years later, light, and millions of years later, stars and galaxies. As a result of the expansion caused by the Big Bang, we can see other galaxies moving at high speeds. And so, 1 billion years after the Big Bang, the universe as we see it came into existence. But what do we mean when we talk about the observable universe? The part of the universe that we can see may not be very large. It's actually about 93 billion light-years. What each of us sees is the matter and energy that fills space. Surprisingly, the fraction of ordinary matter that makes up stars and planets is tiny compared to the hypothetical dark matter we have yet to detect. However, the most interesting thing we know about the universe is life. According to the principles of physicist Brandon Carter, we exist as observers, and the universe conforms to our existence. And the universe must be like observers. That is, the universe can be such that our existence is possible. This leads to the fundamental question: does the universe exist apart from us? Let's turn to quantum theory. Physicist John Wheeler, colleague of Albert Einstein, modern observations suggest that they can influence the behavior of photons. A famous experiment with photons directed at two pieces, and a screen shows that observers with detectors can influence the behavior of photons. Thus, if there are observers, the photons act like particles and pass through one of the two slits. However, without observers, the photons behave like waves and pass through two slits at once. Wheeler decided to take the experiment to the cosmic plane, pointing the photon gun at the quasar and moving the slits to two nearby galaxies. Thus, the photon may have started billions of years ago, before life and the development of photon detectors, forced to go to those detectors. That is, the motion of light always depends on the observer. Does this mean that the universe cannot exist without humans? Not really. It is true that humans are capable of receiving information, analyzing it, and reproducing it for others. But they are not the only watchers, even if they are perfect. Following Willer's model, high-energy particles, which can exist in different states, can interact with rocks on Earth. Thus, the stones will leave a trail of particles, which means that new information has been exchanged. Therefore, according to this hypothesis, the universe does not need consciousness. Another experiment in quantum mechanics confirms this. 3 scientists who recently shared the Nobel Prize, John Clauser, Alain Aspect, and Anton Zeilinger, were able to prove that the universe is not local. This, of course, does not mean that the universe as we know it does not exist. Physics distinguishes between the principles of reality and locality. Reality means that an object exists and does not change its properties even if no one observes it. A red apple will remain with or without measurements. Area, in turn, is explained by the fact that objects can be affected only when they are related to each other. And these distant bodies cannot interact with each other, for example, at the speed of light. If you send a light signal to a friend 10 light years away, you won't get a response after turning on the flashlight. This leads to the principle of local realism or the principle of hidden variables, according to which objects with certain characteristics exist at some intangible level and are independent of observations. In other words, we live in an objective reality with a certain set of factors, independent of our consciousness. But physicist John Stuart Bell disagreed. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper under the acronym EPR, in which the theorists attempted to prove the absurdity of quantum physics. They questioned the possibility of quantum communication. If 2 particles are bound, they are conserved even if they are in different parts of the universe. For example, if a particle rotates clockwise, other particles associated with it rotate counterclockwise. So, if one piece is on Earth and the other piece is 1,000 light-years away, then, knowing the direction or rotation of one of them, one can immediately know in which direction the other is rotating. This contradicts GR because nothing can travel faster than light. So, 30 years after EPR was published, Bell conducted a thought experiment. He continued with the EPR idea, but refined it a bit. He envisioned 2 observers, Alice and Bob, in different parts of the solar system and with particle detectors, but with 2 different settings, A, B, B, for more precise observations. Thus, if the local theory of reality were true, one particle would have no way of knowing what parameters another has. Results are always random. If quantum theory is correct, then the particles would be perfectly correlated. 3 Nobel laureates, Clauser, Aspect, and Zeilinger, were able to replicate the experiment in reality. By counting the number of times Bob and Alice agreed with each other about the state of the particles, they confirmed Bell's theorem, proving that the universe is not locally real, meaning that everything in the universe needs an observer. That's why we can breathe. The universe exists as we think it does. However, what if I told you that this might not be the case and that our brains are deceiving us? From our perspective, according to Einstein's GR, the universe is a continuum of space-time with 3 dimensions and 1 temporal dimension. All massive objects in our universe, including our Earth, can cause gravity to dissipate time. Yes, we monitor all of this. What could be cheating? Perhaps our 4-dimensional universe is a holographic projection. It sounds fantastic, but this theory is being seriously considered by scientists. Everyone has probably seen a hologram, a deep 3-dimensional image created on a flat surface using light. The light produced by the holograms contains a large amount of encoded information. For example, texture or relative distance. Thus, From all angles, the image will appear three-dimensional. Theoretical physicist Juan Maldacena suggests that our universe might be like this. Everything you see in 3 dimensions is in 2 dimensions. Black holes helped develop this idea. Black holes can increase their mass at the expense of other objects falling onto them. But these objects do not disappear. They remain in the black hole. But black holes can decay. Renowned physicist Stephen Hawking discovered that black holes evaporate and then disappear completely. What happens to data that falls into a black hole? Will it be gone forever? This goes against the basic laws of physics because matter cannot disappear. They change to another state according to the principle of conservation of mass. However, the idea of the holographic nature of the universe can solve this paradox. The holographic theory is explained through the hypothetical doubling of 2 other mathematically equivalent theories, the ADS-CFT correspondence. Anti-de Sitter space, ADS, a space closely related to negative space and constant theory, has a curved parabolic shape in more dimensions than required by line theory. This space is often defined as 5 dimensions, but it can have up to 10 dimensions. ADS also has limitations, unlike the popular model of the universe. Modern cosmology suggests a flat universe model, similar to a simple universe, where 2 lines or 2 light waves will always be parallel. If the universe is truly perfect, it may not have boundaries. But it's possible that our universe is so warped in unimaginable disintegration that satellites can't see it. Therefore, the UDS can be thought of as a 3-dimensional ball with a finite surface, but it is very flat. This theoretical limit is crucial for the second theory in this theory, conformal field theory. CFT describes the behavior of particles and fields in flat space and is one-dimensional compared to ADS and has no particular gravity. So there is a dualism that allows us to look at the system from 2 sides. Internally, what is in ADS can be translated to CFT and vice versa. So their duality is like a borderline hologram, encoding everything inside. Thus, according to ADS-CFT, information entering a black hole does not disappear without a trace. Information can be encoded in the 2-dimensional event horizon of a black hole, beyond which the gravitational disturbance is so strong that even photons cannot escape. Thus, the data is not lost, only moved up. This duality theory does a good job of explaining these and other modern mysteries of the universe, but it has several problems. For example, the ADS-CFT correspondence works in a negative spatial constant universe model. However, according to current observations, our universe has a positive constant value and is still expanding. So, we probably don't live in a finite universe. For example, in 1929, astronomer Edwin Hubble concluded that the universe was continuing to expand and that this process could continue forever. Therefore, since our observations are limited, the question of the infinity of the universe remains open. This point is crucial to the whole theory. So now the idea of ADS-CFT has mathematical value. But if we can find answers to all the findings of the theory, we can prove that the universe is a hologram. The question of what our universe is worries not only physicists, but also philosophers. In 2003, philosopher Nick Bostrom suggested that some scientists, such as Elon Musk, think it's somewhat possible. What if we are living in a simulation? In his paper, Bostrom argues that one claim about simulation capability must be true. First, humans will die before they reach a technological level that would allow them to create the most complex simulations. Second, it is highly unlikely that an advanced civilization would be interested in imitating its history. 3 advanced civilizations are creating simulations, and we live in one of them. So, if the third idea is true, we could live in a completely simulated world like computer games. Of course, this hypothesis cannot be tested empirically, but we may have some evidence to support the simulation hypothesis. About the speed of light. According to Einstein's theory, we know very well that the speed of light is limited to 186,000 miles per hour. Therefore, all the light we see from the stars takes a long time to reach us. A simulated device cannot have unlimited computing power. There must be some limits, and it's these limiting artifacts that we can observe at the limit of the speed of light. So, if this hypothetical computer processor running the simulation could perform one operation per second, it will have a warranty of 186,000 miles. In particular, the simulation can also explain the principles of quantum mechanics. As with subatomic particles, we define their state by looking at them. Thus, based on the simulation hypothesis, we see only the indicated part of the universe graph, and the rest of the graphs remain empty. And yet, despite the interesting explanation, by limiting the speed of light, a simulated universe is considered a speculative hypothesis because it cannot be proven or disproved. Maybe someday, if this hypothetical computer matrix starts to fail, we'll reconsider this idea. So, the universe is still a great mystery to us. We cannot believe that everything we see is not an illusion. As we have said, we are aliens to the universe, but what if we should never live? The Earth, the Sun, and our galaxy were never meant to be. CERN scientists believe that symmetric matter and antimatter must have been created after the Big Bang. So, if this scenario were to happen, all the particles had to come together to destroy the whole. However, something has created an imbalance between the two substances, and it is not yet known what it is. So we can say we are happy because we are here now, and we would be able to observe the universe and discover all its secrets. Do you think that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the force that governs our existence and seems to dictate the rhythm of our lives, is not what it seems. For example, time seems to slow down for objects traveling near the speed of light, and it flows at different speeds depending on the force and gravity around us. Have you ever considered that time may be a figment of our imagination, a construct our brains come up with to make sense of the world? In search of the truth behind this mysterious concept, you will have to step into the unknown and question everything you know about time. Time, in its simplest form, is a tool we use to measure change and organize the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles, like day and night, or the changing of the seasons. It was important in coordinating activities such as farming, navigation, and religious rituals. Early methods of telling time were based on natural phenomena, such as sunrise and sunset, the phases of the moon, and the positions of the stars. As human society has become more complex, so have our ways of measuring time. To divide the day into smaller and more manageable parts, we developed instruments such as sundials, water clocks, and finally, mechanical clocks. Calendars are designed to track the passage of long periods of time, such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of people's understanding and interpretation of time. Although timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brain processes and interprets time differently, depending on factors such as age, emotional state, and cultural background. This suggests that time is not a fixed universal phenomenon, but a flexible construct shaped by our experiences and needs. Despite the presence of time in our lives, it remains a somewhat illusory concept. This begs the question, is time an objective reality, or is it a construct created to bring order to our chaos? So, let's look a little deeper into the history. The traditional understanding of time as an independent, constant entity was challenged by Albert Einstein's groundbreaking work in the early 20th century. Einstein's theory of relativity introduced the concept of time as a measurement, forever changing the way we think about this mysterious phenomenon. Einstein's theory of relativity arose from the nature of light and the concept of absolute space and time that was central to classical physics. He argued that the laws of physics must be the same for all observers, regardless of their relative motion. This revolutionary idea led to the development of two related theories: special relativity and general relativity. In his theory of special relativity, Einstein showed that space and time are not separate entities, but are bound together in a single continent called space-time. In this four-dimensional frame, time is transformed into a fourth dimension, and events are represented as points in space-time. This concept overturned the traditional view of time as an independent variable, showing that it is an integral part of the structure of the universe. Einstein's theories also showed that time is relative and depends on the reference of the observer. According to the theory of special relativity, two events that appear to one observer at the same time may appear to move relative to the first to a second observer at different times. This phenomenon, also known as relative relativity, makes it difficult for us to perceive time as an absolute and constant unit. General relativity extended the ideas of special relativity and brought gravity into the picture. According to this theory, large objects such as planets and stars cause periodic distortions, and this vein is captured by the force of motion in it. The presence of a large object can also affect the passage of time, resulting in a phenomenon known as gravitational time dilation. According to the theory of special relativity, time dilation occurs when two objects are moving at relatively high speeds relative to each other. If an object is moving faster, time passes more slowly compared to a stationary observer. This effect becomes apparent when approaching the speed of light. This phenomenon is best illustrated by the famous twin paradox. In this case, one twin travels close to the speed of light, while the other twin remains on Earth. Upon return, the traveling twin will be younger than the earthly twin due to the time difference. In general relativity, time dilation is also caused by gravity. Time moves more slowly in stronger gravitational fields, such as near large celestial bodies such as planets or stars. This effect was tested experimentally using atomic clocks located at different altitudes. Clocks closer to the Earth's surface run slower than clocks at higher altitudes where gravity is stronger and gravity is weaker. Time dilation, although seemingly illogical, has been experimentally verified and has practical applications. The best example is the Global Positioning System, or GPS. Earth-orbiting GPS satellites experience time dilation due to acceleration and gravity, which must maintain accurate time and location. Furthermore, gas pedal experiments for high-velocity particles have confirmed that particles traveling at the speed of light experience significant time dilation, as predicted by the theory of special relativity. Before Einstein's theory of relativity, time was considered the unchanging and universal background for all events in the universe. Isaac Newton, for example, believed in the concept of absolute time, which is uniform and flows independently of the events it measures. However, discoveries related to time expansion. The theories of special and general relativity refute this notion with the relative nature of time, and prove that time is not a constant but a variable quantity depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also implies a strict adherence to casuistry, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events can depend on the reference of the observer, which can lead to cases where cause and effect appear to be reversed or simultaneous. This complicates our intuitive understanding of randomness and forces us to rethink our ideas about the way things work in the universe. The concept of the arrow of time, the idea that time flows in one direction, from the past to the future, based on our understanding of the world, has also been questioned. However, relativity's relativistic nature of time and random reversals force us to reconsider whether the arrow of time is a fundamental aspect of the universe or a construct of human perception. As the traditional view of time as an absolute entity was undermined by the discoveries of relativity theory, some scientists and philosophers suggested that time might be an emergent property rather than a fundamental aspect of the universe. From this point of view, time arises from the connection and interaction between objects and events, rather than being independent of them. Leaving aside the problems of Einstein's theory of relativity, we move into the more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and ambiguous, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic level. It is governed by a set of probability rules that differ from those of classical physics. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition, and their properties can only be determined by measurement or observation. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics describes time as a continuous and absolute unit, quantum mechanics is a fascinating phenomenon in quantum mechanics where particles interact, such that the state of one particle instantaneously affects the state of another, regardless of distance. When two particles combine, their properties combine. If you measure the position of one particle, you immediately know the position of the other, even if it is light years away. This behavior defies classical intuitions about locality and causation, making Albert Einstein's far-fetched work. The consequences of quantum entanglement extend beyond individual particles and may play an important role in understanding cosmic-scale phenomena. The work can provide information about the behavior of particles in extreme conditions, such as in black holes or in the early moments of the universe after the Big Bang. As the universe expanded rapidly in the early moments of its creation, bound particles could interact rapidly, creating correlations that shaped the distribution of matter and energy throughout the universe. In addition, researchers are investigating whether quantum mixing contributes to cosmic-scale structures, such as the formation of galaxies or the distribution of dark matter. Some theoretical models may involve processes such as inflation, the rapid expansion of the universe, that may underlie the large-scale structure we observe. It shows how these connections can be fundamental to understanding not only microscopic quantum systems, but the vast contents of the cosmos. The study of quantum entanglement in relation to cosmic-scale phenomena also raises profound questions about the nature of reality. It challenges our traditional views of individuality and interconnectedness, suggesting that the fabric of the universe may be more interconnected than previously thought. When researchers explore these connections, they enter the territory where quantum mechanics and cosmology converge, inviting a deeper understanding of the universe and its fundamental principles. Quantum tunneling is a remarkable phenomenon in quantum mechanics where particles can pass through energy barriers that they would not have to cross classically. In the classical sense, a particle requires enough energy to overcome a barrier, and if it doesn't have that energy, it remains bounded. However, in the quantum realm, particles are described by wave functions, which correspond to the probability of being located. This inherent uncertainty allows particles to tunnel through barriers, emerging on the other side even though they normally do not have enough energy to overcome the barrier. To illustrate this, imagine a ball rolling with a hill in front of it. Classically, if the ball doesn't have enough energy to hit the top of the hill, it will bounce back. However, in quantum mechanics, the ball can appear on the other side of the mountain with a non-zero probability. This effect relies on the wave nature of particles and is most noticeable at microscopic scales where quantum effects dominate. Quantum tunneling has profound cosmic implications. For example, it plays a key role in nuclear fusion, which powers stars. In stars, hydrogen nuclei must overcome the Coulomb barrier due to their positive charge to fuse with helium. Quantum tunneling allows these protons to penetrate this barrier, allowing for coupling at different temperatures and energies. This process is essential for the production of energy in stars and directly affects the evolution of galaxies and the synthesis of heavy elements essential for life. In addition, quantum tonnage can provide information about phenomena such as cosmic inflation, the rapid expansion of the universe after the Big Bang. Some models suggest that quantum tunneling mechanisms could support the multiverse concept and create multiple universes. In this sense, tunneling affects not only individual particles, but also the creation and evolution of the universe. As our understanding of quantum tunneling grows, its cosmic significance reveals a deep connection between the fundamentals of quantum mechanics and the evolution of space. A quantum vacuum, often described as the lowest energy state of a quantum field, is an interesting concept in quantum field theory. Unlike the classical concept of a vacuum, the quantum vacuum is filled with activity. It is filled with virtual particles, which have become increasingly popular due to the uncertainty of quantum mechanics. These tiny particles exist for such a short time that they cannot be observed directly, but their effects can be felt by influencing various physical phenomena. One of the interesting aspects of the quantum vacuum is its role in energy conversion. These fluctuations create phenomena such as the Casimir effect, where two conducting plates in a vacuum experience an attraction due to the compression of virtual particles between them. This effect shows that the quantum vacuum can have measurable effects on physical objects, suggesting that empty space has no activity. The consequences of the quantum vacuum extend to the larger structure and evolution of the universe. In cosmology, vacuum energy is thought to be associated with dark energy, a mysterious force that drives the universe's acceleration. The energy density associated with the quantum vacuum can support this process, suggesting that the cosmic fabric has energetic properties that shape cosmic dynamics. As the universe expands, the quantum vacuum may play an important role in determining the formation and evolution of structures such as galaxies and clusters over space-time. In addition, the quantum vacuum may affect the early moments of the universe after the Big Bang. A rapid expansion called inflation can affect the high energy conditions that exist in the quantum vacuum, leading to the large-scale structure of the universe as we observe it today. Ultimately, understanding the quantum vacuum helps bridge the gap between quantum mechanics and cosmology, revealing how the fundamental properties of space and energy affect the history and structure of the universe. As we delve deeper into these concepts, we uncover the intricate connections that bind the fabric of reality together. Quantum mechanics and general relativity represent the two main pillars of modern physics, but they operate on very different principles. Quantum mechanics describes the behavior of particles and their interactions on very small scales, and general relativity describes gravity as the curvature of time caused by mass and energy on cosmic scales. Reconciling these two theories has proven to be one of the most important problems in theoretical physics. On cosmic scales, gravity primarily occurs in regions where gravity is unusually strong, such as black holes or the very universe. In these situations, the assumptions of general relativity break down, leading to a singularity where the laws of physics work as we know them. Quantum mechanics allows for uncertainty and probabilistic results that are not easily reconciled with the deterministic nature of general relativity. This dichotomy suggests that a more comprehensive framework is needed to integrate these two domains. The pursuit of a quantum theory of gravity seeks to bridge this gap. Several approaches are studied, including string theory and cyclic quantum gravity. Line theory states that the main components of the universe are one-dimensional lines rather than points, allowing us to describe gravity and other fundamental forces within a single theoretical framework that accommodates both quantum mechanics and the geometric nature of space-time. DAO. At the same time, loop quantum gravity attempts to calculate itself, which consists of discrete spatial structures that can resolve singularities and provide a coherent description of gravity at the quantum level. Furthermore, concepts such as the information paradox associated with holography and black holes challenge our understanding of information and its conservation in quantum mechanics. The holographic principle suggests that information in the volume of space can be represented as a theory that resides within the boundaries of that space, bridging local and non-local concepts. As researchers explore these and other avenues, there is hope that a deeper understanding of quantum mechanics and general relativity will provide a unified view of the universe that spans both minuscule and cosmic scales. This reconciliation promises not only to deepen our understanding of fundamental physics, but also to shed light on deep questions about the nature of reality. The idea that quantum effects can create connections between distant parts of the universe, or even separate universes, arises from unique principles of quantum mechanics, particularly quantum entanglement and non-locality. In quantum mechanics, entangled particles maintain correlation, meaning that a change in the state of one particle instantly affects the state of the other, regardless of the distance separating them. This phenomenon raises interesting possibilities for how information and influence can travel across spatial distances. Quantum particle interactions challenge traditional local concepts by showing that they extend beyond familiar spatial boundaries. Some physicists hypothesize that this information or influence can be transmitted over long distances, unconstrained by relativistic limits, such as the speed of light. This concept leads to interesting debates about the nature of spacetime and causation, which raises the question of whether it can serve as a mechanism of extensive communication within the universe. In addition, quantum mechanics can provide a basis for the interrelationships between these realms, rather than the concept of a multiverse with multiple universes with different physical laws or constants. In some interpretations of quantum mechanics, such as the many worlds explanation, each quantum event creates a propagation of reality. This suggests that there may be interactions or connections between these industries, potentially influencing the universe. These interactions may produce observable effects, although their detection remains an important challenge. It should also be noted that there are theories that propose mechanisms that can influence spatial structures. For example, some researchers believe that quantum entanglement may have played a role in the coordinated behavior of particles and fields in the early universe. This may help explain phenomena such as cosmic inflation or the uniformity of the cosmic microwave background radiation. Although these concepts still face many challenges in terms of theoretical and empirical verification, they represent profound implications for quantum mechanics. They invite exploration into the fabric of reality, urging us to rethink the structure of the universe and its potential connections. As the dialogue between quantum physics and cosmology develops, these ideas may pave the way for a unified understanding of the cosmos. Negative mass is a hypothetical concept that appears in some theoretical frameworks within physics. It refers to the shape of a mass in reaction against the forces acting on it, compared to a simple positive mass. For example, if a particle with a negative mass were to be pushed, instead of accelerating in the direction of the applied force, like a positive mass, it would accelerate in the opposite direction. This consistent behavior defies our usual understanding of mass and forces in classical and relativistic physics. In theory, negative mass can lead to strange and complex scenarios. For example, if negative mass is present and interacts with positive mass, it can create unique dynamics. A classic thought experiment involves a scenario where positive mass attracts negative mass. In such a case, the negative mass can accelerate towards the positive mass, and the positive mass can move away from it. This can lead to a runaway effect, where the system can amplify itself indefinitely, raising questions about stability and causality in physical systems. The implications of negative mass extend to debates about gravity and cosmology. Some scientists speculate that if the universe has negative mass, it could affect the dynamics of cosmic structures, possibly explaining phenomena such as dark energy or the acceleration of the universe. Integrating negative mass into our understanding of gravity could redefine the concepts of gravity and repulsion, potentially leading to new insights into the nature of cosmic forces. However, it should be noted that negative mass has not been detected or observed in empirical experiments to date. Although some theories in general relativity and quantum field theory accept the concept of exotic matter, the materialization of negative mass remains speculative. Nevertheless, studying the theoretical framework of negative mass helps broaden our understanding of the behavior of the universe and influences the search for a more complete understanding of fundamental physics and cosmological phenomena. Indeed, the possibility of forms of matter different from what we observe is an active area of research in theoretical physics. Although we are familiar with simple matter composed of atoms, composed of protons, neutrons, and electrons, there is reason to believe that the universe could harbor exotic forms of matter with unique properties. One such example is dark matter, which is thought to make up about 26% of the mass energy of the universe. Dark matter does not interact with electromagnetic forces like ordinary matter, i.e., it does not emit, absorb, or reflect light. This means that it remains invisible, only detectable through gravitational effects on visible matter such as galaxies. While the exact nature of dark matter remains elusive, leading candidates, including weakly interacting massive particles and axons, would both have properties and interactions that differ from those of ordinary matter. In addition, researchers are exploring the concept of exotic matter, which may include matter with negative mass or an unusual state configuration. For example, some theories propose the existence of quark matter, in which quarks, the basic constituents of protons and neutrons, exist in a free state without being constrained by standard atomic structures. This phase of matter can exhibit properties that are very different from what we experience every day. Another interesting category is supersymmetric particles that arise in supersymmetry theories. These hypothetical particles would have unique properties, be heavier than known particles, and interact with forces differently. If discovered, they could change our understanding of fundamental forces and particles. The study of these forms of matter invites speculation about the nature of the universe and its potential configurations. It challenges our traditional views and encourages scientists to look for new physics outside the standard model. The exploration of exotic matter not only expands our understanding of nature, but also opens up questions about the fundamental principles that govern the universe and the potential for phenomena beyond current observational capabilities. As researchers delve deeper into these mysteries, they come closer to answering deeper questions about space and our place in it. Mirror matter is an interesting theoretical concept that suggests the existence of a parallel form of matter that resembles ordinary matter but has opposite properties. The idea arises from some extensions of the standard model of particle physics, particularly those related to parity. Parity in physics refers to the symmetrical nature of physical processes. The laws of physics must remain unchanged when spatial coordinates are reversed. However, when the pairing is broken, as seen in the weak interaction, it leads to interesting speculations about the existence of a mirror counterpart to ordinary matter. In this network, the mirror material will consist of particles that reflect the properties of familiar particles such as electrons, protons, and neutrons, but with opposite interactions and potentially different charges. For example, mirror electrons can interact with mirror protons to form mirror atoms, creating a parallel universe of mirror matter. One of the remarkable properties of mirror matter is that it will not react strongly with ordinary matter under normal conditions, making it difficult to detect. This lack of interaction suggests that it coexists with our universe without being observed. Interactions between mirror matter and ordinary matter are likely to be rare, if real, primarily through very specific interactions via gravity or hypothetical intermediate particles. This concept raises interesting and complex questions about the nature of our universe. For example, if mirror matter contributes to dark matter, its gravitational effects may occur through electromagnetic interactions without being detected. In addition, some theoretical proposals suggest scenarios where mirror matter could explain cosmic phenomena, such as the observed asymmetry between matter and antimatter or the nature of dark energy. Alternatively, interactions with mirror matter can potentially lead to observable results in high-energy particle collisions in accelerators or extreme astrophysical environments. While matter remains a speculative concept without empirical confirmation, it offers a tantalizing way to study the nature of the universe and prompts a deeper investigation into the fundamental forces that govern our reality. As researchers continue to explore these ideas, interactions between our familiar universe and potential mirror counterparts may illuminate new aspects of fundamental physics and space. The concept of entire galaxies or cosmic structures composed of exotic matter is an intriguing and speculative idea that stems from the expansion of our universe. Exotic matter refers to hypothetical forms of matter that have unusual properties that differ from normal matter. Exotic matter includes theoretical forms such as negative mass, quark matter, and even mirror matter. While we have yet to directly observe such materials, the thought of their potential existence opens up interesting possibilities for the nature of space structures. If exotic matter is present, it may influence the formation and evolution of galaxies in unique ways. For example, consider a galaxy with negative mass. In theory, such a galaxy could have a completely different arrangement than typical galaxies, as particles with negative mass would resist gravity. This interaction can have a repulsive effect, possibly forming large structures that spread out rather than collapsing under gravity. Such a formation would challenge our current understanding of galaxy dynamics and stability. Moreover, the existence of exotic matter may provide alternative explanations for current mysteries in cosmology. For example, if a fraction of dark matter should be composed of exotic matter, this could help explain the discrepancy between observed gravitational effects and predictions from standard models of galaxy formation. Exotic matter, such as quark matter, can behave uniquely under extreme conditions, possibly affecting the rate of star formation or the distribution of matter within a galaxy. Moreover, if we expand our view beyond individual galaxies to consider larger cosmic structures, the interactions between ordinary and exotic matter can have surprising consequences. For example, a cosmic web formed by a mixture of exotic and normal matter may exhibit unusual properties, affecting the expansion of the universe or creating new interactions with gravitational waves. While the idea of galaxies made of exotic matter remains in the realm of speculation, it expands our understanding of cosmic formations and encourages researchers to explore unusual avenues of theoretical physics. Exploring the potential consequences of exotic matter invites us to reconsider the fundamental properties of the universe, revealing hidden complexities that could change our view of galaxy formation and cosmological order. As knowledge of fundamental physics grows, the idea of such exotic structures may resonate within the broader space exploration framework. Exotic forms of energy, such as dark energy, play an important role in the evolution of the universe. Dark energy is a mysterious force that makes up about 70% of the universe. It is responsible for the rapid expansion of space. As the universe continues to expand, the influence of dark energy becomes increasingly important, further separating galaxies and shaping the large-scale structure of the universe. The presence of dark energy changes the dynamics of cosmic evolution. The early universe was dominated by gravity, which formed matter into structures such as stars and galaxies. However, as dark energy becomes more visible over time, it resists gravity, causing an expansion that appears to accelerate. This has profound implications for the fate of the universe, affecting the interactions and eventual evolution of galaxies and clusters over billions of years. In addition, other exotic forms of energy may affect the universe in different ways. For example, ideas about modified theories of gravity may not yet be fully understood. Such theories can influence the behavior of dark energy and the formation and evolution of structures. Although dark energy is the most studied, the universe may hold other surprises waiting to be discovered, deepening our understanding of cosmic evolution. Understanding these exotic forms of energy challenges not only our view of the universe's past, but also our notions of its ultimate fate. Will the expansion continue indefinitely, leading to a cold and desolate universe? Or can we discover new forms of energy that can change this trajectory? The answers to these questions will change our understanding of space and its continuous journey through time and space.